Hello everyone, my name is Andrea Caprotti. I'm a physics graduate student at the University of Milan, and for this Quantum Future Academy challenge I try to solve the triple well problem. The problem consists in a potential made up of 3 Gaussian wells, and the objective of the task is to try optimize the time and fidelity in the transfer from the first to the final well by modulating the heights of the 2 barriers that distinguish the 3 wells. I treated the problem starting from the heuristic observation that the way the wave function flows from one well to the next is similar to the way a series of canal locks work. And so I treated the problem in a heuristic manner by considering the wave as an actual liquid wave and the barriers and the potential barriers as a set of locks. This certainly is not an exact approximation, but it was helpful in order to visualize the way the wave function passes from one well to the next. The time at which the first barrier is raised and the second is lowered is the optimal time for the second well, as we can imagine all the liquid has flowed in the second pool. In order to respect the symmetry of the system, I decided to use the same characteristic time for both the first and the second barrier, as well as the same potential intensity. We can see on the right how the wave function flows from one pool to the next and how the fidelity changes over time. By changing the potential intensity, we can see how the maximum fidelity changes, and so does the optimal time. And we can see that there's a trade-off between low intensity, which guarantees a higher fidelity, and a higher intensity, which instead returns a quicker time of transfer. So a good trade-off is set between 3 and 3.5 units of intensity. These considerations were made for a single particle wave function. When we consider, for example, a Bose-Einstein condensate, we have to add a nonlinear term in the Hamiltonian, controlled by the parameter beta, which we can interpret like a viscosity parameter. So, as the parameter beta increases, we have a denser, thicker liquid, which, as we can see, cannot pass from one pool to the other with great ease. And so we have to consider a strategy in order to help the wave function flow from one pool to the next. At first, I tried with 2 different strategies. One was to set 2 different characteristic times, and so to lower the second barrier before the first one is raised, and the other was to add an harmonic oscillation to the second barrier in order to act like a steering mechanism for a thicker liquid. In the end, the best strategy was actually the simplest, and it was the one to lower more the barrier, as in to help this liquid distribute more uniformly inside the potential well. And we can see that it actually moves more like a realistic liquid. It sloshes around inside these pools, and at one point it reaches the maximum. We can see that, especially at great value of beta, the fidelity is much less than the previous case, but it's still a better result than without any modulation, in which the liquid does not flow at all from the first to the other 2 wells. And then we can see that the time it takes, it's actually similar to the one considered for the single wave function. That was all. This was my attempt to use a heuristic interpretation in order to help me visualize the results. It certainly wasn't very rigorous, but it helped me to look at this problem quickly and with sufficient results. Thank you for your attention.